of our project is closed loop V by F control of induction motor using space vector modulation on STM32F4 microcontroller. So first of all, allow me to introduce our apparatus. Here you can see that we have a three-phase inverter coupled with a single phase rectifier. This is our microcontroller STM32F4 on which we have implemented our space vector modulation algorithm. Here is the induction motor which is being controlled using the space vector modulation, and this is the DC generator which is mechanically coupled with our induction motor, and here is the electrical load connected to our DC generator. Now first we will see the waveform of space vector modulation. Here you can see that this is the line-to-line voltage waveform of our microcontroller filtered at 50 Hz. You can see that our signal consists of least number of harmonics, or we can say that it consists of least value of THD, total harmonic distortion. Waveform resembles close to the sinusoidal, which verifies our space vector modulation implementation. Now we will introduce the functionality of our project. Here you can see that we have the input speed which has the unit of RPM. This is the input speed which is fed to the microcontroller, and this generates an error signal. And here you can see we have an analog knob which is interfaced with the analog to digital converter to vary the input speed. Here you can see that input speed is varying up to 1500 RPMs, which is the rated speed of our induction motor. We have programmed it in the parameter initialization of our codes. Here you can see that I am varying and decreasing the magnitude, and now it has a negative sign, that is the speed will be minus 1500 RPM but in the opposite direction. So we have a bidirectional speed control here. Using the analog knob, we have linearized the voltage variation because of the analog knob. Now let's turn it on. So first of all, allow me to introduce our feedback topology. This is the proximity sensor whose output is fed to the microcontroller, and the digital sampling is done to measure the speed, and then it is fed to the space vector modulation algorithm which generates the corresponding PWM signal, which is amplified by our inverter and fed to the induction motor. Let's turn it on now. Here you can see that the induction motor is running at the input speed fed by the microcontroller. At present the speed is about 300 RPM. Here x_2 is the feedback speed which is being measured by the proximity sensor, and this is the input speed which is set by the analog knob, and the difference is the error signal which you can see here. The tolerance of the error signal is about 5 RPM. That is, whenever the error increases beyond 5 RPM, it will generate an actuating signal. Now I'm changing the speed through the input signal generated by the analog knob, and here you can see the speed is varying. It is about 500 RPM, and you can see that the electrical load is also glowing. Now I will change the magnitude with my analog knob, and the correspondingly speed will reduce to 0, and then it will start rotating in the opposite direction at about minus 1500 RPM. Here you can see the measured speed and the input speed, minus 1500 RPM, minus 1500 RPM. Now I will change the magnitude again using my analog knob. The beauty of this algorithm is, no matter whatever the mechanical load is connected to our induction motor, using the closed loop we can obtain the precision and accuracy in the speed adjustment. Here you can see that the input speed is very close to the measured speed even though the mechanical load is connected. So our speed variation is independent of the mechanical loading. This is the basic advantage of closed loop topology in variable frequency drives. Now here you can see that we have a pulse. The motor is rotating at about 1500 rpm, and this is the output pulse of the proximity sensor. By measuring the distance of this pulse, we can calculate the speed. The circuit is as follows. The output of the proximity sensor is given to the comparator of op-amp, and then it is fed to the TLP250, which is the optocoupler. By measuring the time duration between these two pulses, we can measure the speed. Now let's introduce the next functionality, which is the programmed AC drive. Here you can see that we have two arrays. First array corresponds to the magnitude of the speed at which our motor will be running, and the second array corresponds to the duration for which the motor will be running at that speed. For example, we can look at the first entry here, which is about 200 rpm. So our motor will run about at 200 rpms for 5 seconds. Here you can see that 200 rpm, 5 seconds. Then it will run for 400 rpm for 5 seconds, then it will stop for 2 seconds, and so on. So this is a trend, or we can say that our AC drive of induction motor is programmed, and it will iterate this trend and continue to rotate in this situation. Now let's turn it on. Here you can see that it is rotating about 300 rpm according to the speed input given in the input array, and now it will accelerate after some time. It will stop for 2 seconds. Now it is running at 1500 rpm according to the speed input. Now its speed is reduced to 300 rpm. Now it will stop for 2 seconds, and it will rotate in the opposite direction at 300 rpm. Now it is rotating at the minus 1500 rpm. You can now see also the electrical load glowing. So this is the trend which is set by the two input arrays. One is of the speed input, other is of the time input, and it is repeating the trend set. Thank you very much.